In this video, we are breaking down gradient descent, the code algorithm, the optimization engine behind most modern machine learning algorithms. In our linear regression video, we discussed about this problem, where given the house area, number of bedrooms, number of toilets, number of balconies, we were predicting the house price. So we were given one data set of n samples x1, y1, x2, y2 till xn, yn, where xi's are d-dimensional because we see we have 1, 2, 3, 4, 4 input variables, and based on that we are predicting the output, that is house price. So yi is the output labels we got, and this is a real value for all I equals to 1 to n. So this is the predicted output we found, that is function of xi, that is xi is a d-dimensional vector. So this is a function of d values. So in a d-dimensional space, we got w0 plus w1 xi1, w2 xi2 till wd xid, which we simplified as w0 plus summation of wi xik, where k is the dimensions. For each samples, we have simplified it further. So we got one X matrix. This is for n samples. It has n rows, and each row is for each data sample. And this is the W vectors we got. So XW, this is the predicted output we got, and Y, that is Y1 to Yn, these are the actual output for n data samples. And our objective function was to minimize this sum of the squares, right? So norm of xw minus y whole square. So the difference between these two, square difference between these two. Now this is the square error, and also we can divide it by n and we can get the mean squared error. So either of one of this we can try to minimize. Also, we got the value of w by solving this objective function, that is x transpose x will inverse x transpose y. But to solve this, x transpose x has to be invertible, and otherwise we have to calculate the pseudo inverse. And also we saw if the data set is large, this computation will be highly expensive. So we cannot, for a large data set, we cannot just use this computations to get our W. So you see this objective functions, so this norm squared error, right, or mean squared error. So this is a squared function, this is a convex function. So in a two-dimensional case also, if you take a square function, it will look something like this, right, y equals to x squared, let's say, if we're taking. So this is a convex function. So for a convex function, we can use an iterative algorithm like gradient descent, which works for convex function. So how it works? So to find an optimal W, we start with some initial Wt and update in each iteration. So Wt plus 1 equals to Wt minus something. So that's how we are updating our W in each iteration. So how we are updating? So this is the error term, right? So the difference between the mean squared error basically for linear regression. We are taking the gradient of it. Basically we are taking some multiple of this gradient and we are deducting from the previous W, and that's how we are getting the current W. So let's think about this gradient first. What is this gradient? So the gradient represents slope and points in the direction of steepest ascent. So let's try to understand this. So if this is a convex function, for simplicity I have taken in 2 dimension. So what is the gradient? Gradient represents the slope. So at this point, this is the gradient. At this point, this is the gradient. So this is a positive gradient in this direction and this is a negative gradient in this direction. And if you see this convex function, it has minimum at this point. So if you are at this point with positive gradient, we have to move in this direction to reach then this minimum point. If you are in this point, then to reach this local minimum, we have to go in this direction, right? So if the gradient is positive, we'll move in the negative direction. If the gradient is negative, we'll move in the positive direction. So that's why we are deducting some multiple of this gradient from W at each iteration. So next, let's see here. So let's say we are initializing W and with that initial weights, we are getting some loss function. So that is here. So this is the gradient here and this is the minimum loss or error. And from this initial position, we are taking incremental steps to reach this minimum point. Now, what is this alpha? So we are deducting some multiple of this gradient, right? So this alpha is called the learning rate. It decides how fast we should move to reach this minimum point. So if alpha is very small, then we'll take small baby steps to reach the minimum. So that means we'll have more iterations and it will take more time. If alpha is too large, then let's say we are starting from here, and of course you have to move in this direction, but instead of reaching here, you are overshoot and we reached here. Then from here to here, here to there, right? So instead of converging, you are diverging. But if the alpha is proper, just right, then we'll take required number of steps to reach the minimum point. In our upcoming videos, we'll discuss more on this learning rate or how to improve this gradient descent learning part. Now here is the algorithm. So our function is this EW, that is the error function or loss function that we want to minimize, right? So we'll initialize learning rate alpha to be some positive value. Initialize t equals to 0, that is the first iteration, and we'll choose some W0 initial weights for the W. Then we'll iterate until convergence. So this part will repeat. So we'll compute the gradient, this gradient of this error or loss function with respect to W. Then we'll update the parameter, W parameter, Wt plus 1 equals to Wt minus alpha of this gradient. Then we'll increment the t. We'll do this until convergence. After convergence, this error or loss functions will be minimum, and for that the argmin will get Wt. So that will be our return value. So that's how we'll get a proper weight for our model.